Hello again. So this time we have Raphael Pos here from CockroachDB. He's from the Netherlands. He has a PhD in computer architecture, which is quite interesting. He works with compilers and now databases, of course, and he's a major contributor to CockroachDB. He chose as his charity the Electronic Frontier Foundation. Would you like to share a bit on why you chose it?
Thank you, Paula. My choice is motivated by my interest in the impact of the internet on society, and I think that the EFF is a major player to safeguard this. Thank you.
So your talk is on error handlers and pitfalls in distributed Go applications. I think we've all had a few of these issues, and without further ado, I would like to give the stage to you.
Thank you. Let me share those slides. All right. Is everything visible? Yes. So thank you for having me. Thank you for the introduction as well. Today I will share a few things that came from experience, trial by fire, if you will. I will briefly remind, well, set the stage by reminding us of the basic APIs that are provided by the Go language, and then jump into the various concerns that we've discovered along the way in the past few years. And then in the second part, I will talk about what we did about it. So as Paula said, I am from the Netherlands. You can find me on Twitter and GitHub as well. And I publish long form research articles on my website as well. Some of them are Go related. Let's get started. So at the very beginning, what we have historically is this vision that are objects. They are data that can be inspected by programs. And that vision was there from the very beginning. So the standard API is a built-in interface called error in small letters that is visible everywhere, and that only guarantees that error objects have a textual message that can be displayed. And then soon after that, on historical basis, a couple of years after Go started, but a long time ago, the PKG errors package created an extension to that vision that errors are linked lists. And the idea behind this is that it's interesting to be able to decorate errors with additional payloads that describe additional circumstances, for example, stack traces and other things. And that can be implemented efficiently by linking things together. And then it provides a separate internal interface with the public cause method that you can call from your own code to access the next item in the linked list. And then when there is no next item, you have attained what is called the root cause. So it has been there for a long while, and a lot of people use this, and we think it's very good. And then what you see in code that uses this is cases where you have error objects returned by functions, and then some functions have guarantees about the type of errors they return, and then you can cast the error object to get to that particular instance. And then if you are a user of that linked list concept, then you need to use very often a loop to access the different layers in the linked list until you find what you're looking for. And such a loop is now in the slides. There is an iteration across the cause interface. And then whenever you find what you want, usually inside the body of the condition, you have a break to exit the loop. Now, that has been very prevalent for a long time, and it's been so prevalent that the Go developers have recognized, well, this is a bit cumbersome, and we probably want to simplify this. So the Go 1.13 proposal was a subset of a more general project called the Go version 2 error proposal, was to embed some of that wisdom in the standard library. And so they came up with the understanding that linked lists are good, that annotations are good, except that they didn't like the cause methods that the PKG errors had implemented, and therefore they decided to rename it to unwrap. there are reasons. The major innovation was to say all these loops we can simplify by having a common implementation of them, and there are at least two functions of interest, the errors.is and errors.as functions. So error.is is a generalization of making a test on an error object like you have here across all the elements of the loop, and error.as does the generalization of a cast over all elements of the list. So this is very good. This simplifies code. It's the code we had earlier. Instead of a cast followed by accessing the error element of path error, we can simplify with just a single call to errors.is. And then if we want to access a particular field of the path error, we can use errors.as, and those two things are independent of how many layers there are of wrapping around the cause of the error. So that's actually a very nice simplification. What they did not retain, though, from the PKG error implementation and proposal was to also automatically embed stack traces in error objects. And that is very good. Stack traces are very good because when an error happens that is not expected, later on in somewhere else in the system, we discover the error is not desired, and that is a moment where we want to know where it originated. And not having a stack trace inside the object is cumbersome. So that's a bit sad that it was not included. Now that we have set this stage, I'm going to talk to you about errors in practice. So as Paula was saying, I work with Cockroach Labs, and Cockroach Labs makes CockroachDB is a SQL engine. There's also a distributed SQL engine. So that means that there are different pieces of a CockroachDB clusters that runs on different systems of our network. So we have a SQL engine. Now, a SQL engine has tables and databases and things like that, and therefore it also has the ability to create those things and to change them. So they're called schema changes. And those schema changes, for performance reasons, are desired to run on multiple nodes. So what happens when you have a distributed systems, multiple nodes, well, some nodes can fail. There are transient errors. For example, a server is down for maintenance, or maybe there is a network trouble somewhere. And so there are a lot of transient errors all the time. And in order to prevent SQL clients from being affected, we want to retry a lot of operations internally to the database so that the client doesn't notice that there is something amiss. So here is an example such code where schema change that is distributed might encounter a transient error, and we need to decide whether a transient error can be retried or whether it's a permanent error. And so there is this function, is an error permanent? Now, you see here gRPC errors is close connection, and inside that function you will see a call to errors.is and between other things, and it's kind of doing what it should do. But then below that, you see the strings.contains, which is really weird because I just told you a lot about errors.is and the fact that these APIs are good and so on. And then this code here, which is supposed to be state of the art, is not doing this. So what's going on here? Well, the main problem is that this particular error that is supposed to be considered to be non-permanent error is actually coming from a different node of the network. And errors.is doesn't work like this. I will explain shortly why. And therefore, we can't use this in this context, not the one from the Go standard library. And so we make do by doing the other things that we should not be doing. So, well, you would say, well, we should not be doing, but should be fine if it works, right? I mean, that's the thing is that it doesn't work. It doesn't work in a way that is very good, because you can see here an example of a plain valid SQL queries that a client app could send to the database that is especially crafted to contain a copy of that error message. And now look what's going on here. You have a table data that just contains the text of this error message, and then a schema change statement is issued to the database that is asking to create a new column that is a result of converting that string to an integer. Now, converting a string that it doesn't look like an integer to an integer is bound to fail and therefore generate an error, in particular a cast error. And the cast error in Go with the strconf library will copy the text that was trying to be converted, including therefore this entire string. And so here you get an error for a conversion from integer to strings that contains this string. And then you come here, and then this error is considered to be a non-permanent schema change error, and the DDL never terminates because database tries to retry it forever. That is really, really not good. So what we learn here, number one, is that string.contains is really bad for error predicates. So that was something that was already spelled out many places before in the Go ecosystem. And we also learned that it's actually pretty possible in a very reasonable way to design a system to come across a situation where doing so will create a non-expected application bug, something that users are bound to notice and perhaps even turn into security vulnerabilities. So we were not happy about that. So what's going on here, if I want to generalize this a little bit, is that the errors APIs that is provided by the Go language and the other libraries are assuming that error objects are global variables, that you have a single process application, and error.is has been simplified and accelerated to only compare error addresses in memory. But of course, if your error object comes from somewhere else, it's been allocated dynamically and it doesn't have the same address every time you receive it, and therefore error.is doesn't work. So in summary, I have to choose between making my code correct with regards to error handling or distributed. And apparently, according to the natural API definition, I cannot have both. That is very unfortunate. So what you see throughout this library for things that is inherently networked where people care about this, well, they do things. So for example, you will see standard objects in the libraries that have responses to network queries, where there is a response object that is not an error object and contains a payload that describes the particulars of the errors on the other side in a way that is structured, so that is safe. But we lose the error API by doing responses. Another thing that's common, in particular what has been done in other places in CockroachDB and has been done throughout the ecosystem, is using protobuf and having particular error payloads as messages. And so you might define your own error message and then say, well, if I have multiple error types, I will have an enum in protobuf and with multiple various objects here. So that's actually pretty nice. It's properly typed, and then everything looks fine. Then you can also have your own Go file next to it to add your error strings to it. However, we have problems. So we have to list all the errors in the same file. And that means that you end up with having a giant file protobuf that contains all your error types. So it's not convenient from an engineering perspective. The other thing is that the protobuf definition wants to have all the objects that are supported listed in the file. And if it doesn't, if the protobuf decoder doesn't have the definition in the files, and it doesn't know how to interpret something received over the network. And then if you have multiple versions of your source code, well, the old version of the code on one side of the network will not be able to understand the errors from the other side. That is using a new error that is not known to the old version. And then the other thing that we have actually problem is that we have this promise to have linked lists, and unfortunately PKG errors and the error library don't do this. Because we want everything in a single package and we cannot have dependency cycles. And also automatically implementing this unwrap or cause method is actually very complicated with protobuf. So it's just, it doesn't match the reality of the APIs that the Go language wants to provide. So that's the big message here, is that the Go ecosystem today doesn't have good answers for errors in distributed code. What we did about this is oh, I forgot. There are some additional concerns. I'm not going to dwell on them too much, but I do want to insist on those tag traces because they are really good and the Go standard library loses them, and that's really not good. So let's talk about what we did about this. We did some research, and particularly we wanted to have drop-in replacement. So what we did here is the libraries that uses the same API as proposed by the Go standard library, but also adds network portability for error objects. It's a separate component. It's not linked to, it's not tied to CockroachDB. You can use it in your own apps without a dependency in the entire CockroachDB project. So what does it have? Well, on the left side, you have the standard APIs, including the one from PKG errors. You can use the library as a replacement for either. But the new thing is really these two encode and decode methods that convert an error object in the Go language into a protobuf encodable error object. And that logic contains some complexity because we wanted this to work for any error type and not just those that are known to this library. And then on top of this logic, we create a contract that the is and as methods from the API work across encode and decode cycles, including across the network. How do we do this? Well, the magic here is to understand that the API is an equivalence operator, and equivalence is something that is at a high level, a matter of deciding how you want things to be equal to each other. So the Go library decided that things are equal just if they have the same address, but in reality, when you care about error objects, you can be a bit more generous than that, and we have this notion of identity marker. It's kind of a string, and that is used for network errors, and if errors happen to be the same machines, then we can still compare addresses, because if two errors have the same address, they will also have the same marker. So internally, you don't have to look into this now, but we of course have an encoding that look like a linked list. So an error is either a leaf or a wrapper, and if it's a wrapper, it has a cause that is recursively defined. And then this identity marker here is also encoded on the network, so that is always available regardless of whether your objects are protobuf encodable or not. So identity markers, that's the key solution here, like the key idea, is that we are going to use more than just the address of the error. We're going to combine the information about the types of the errors and also the error message. And so if you have two errors, for example, like some two basic types that are different, and you wrap them together, you need to be careful when you do a marker to embed all the types in the chain of errors and not just the leaf one, because if you have the same wrapper, of course, the outer type of the error is going to be the same. So if you want two errors to be different, if they have the same wrapper on the outside, you need to take all the types on the way. So that's what we do. We construct an identity marker using a recursive function that goes through all the types and also captures the entire message. And that is what gets compared with errors.is if the addresses are different. And then if those markers are equal, then the errors are considered to be equivalent. And that conveniently works for most of the interesting errors of the library, like the end of file error doesn't exist, or connection refused, context deadline exceeded, and so on. All this works through this mechanism extremely well. So that's the automatic mechanism, and in some cases, you will see in your own code that you will use some wrapper errors with some payloads that don't participate in the error message, but they also have the same type. And in that case, well, the mechanism I just explained doesn't work directly, and so there is sometimes a need to overload this and override this, and so we have this API to override this default identity marker. And if you recall the Go version 2 API proposals, there is an error.opaque function. Very good reason for it to exist. But if you want that to work properly with this mechanism I was explaining, you need to use errors. We needed to implement this by using errors.mark internally. Errors.as is the other part of the standard library that also powers the errors.f operator. That's a bit more complicated because this really needs Go types. It's not just an equivalence relationship. And if you want to have Go types across the networks, there is no magic here. We need to actually decode the messages into and instantiate local Go types properly. And that we cannot automatically generate today because we can construct type definitions dynamically in the Go language. And so unless your error is local or it already implements proto.message, in this solution we provide, we have to use a registry of encode-decode functions that are able to convert errors into protobuf messages and the other way around. In the particular case where you have error wrappers or leaves that only have a type but don't really have a payload, that's actually pretty common. Then only a decoder is sufficient because we have a default encoder that does this, that does work with any types that doesn't have a payload. The other little problems that I kept under silence includes embedding a stack trace. We made sure that the replacement stack trace mechanism from PKG errors works across the network, so you can get your stack traces after an error has traveled. And something that is pretty important when you start defining distributed systems is having a proper RPC mechanism. Google has a gRPC library, and the gRPC library has a pretty terrible idea of error handling by default. And so we have contributors that gave us some code that allows us to make gRPC do the right thing with regards to errors. And so with that integration, you can get your error payloads conserved exactly from throughout an RPC. That's actually pretty sweet. So this combined errors here API, I mentioned in the slide for later reference. I'm not going to explain it. Please feel free to peruse the slides and the API definition if you want to have more reasons to use it. Another thing that's kind of funny is that there is this comment in the issue about the version 2 error value proposals. I didn't exactly know how to format an error with %+v when you do formatting of strings. And we tried to do it, and we eventually succeeded, but it took us a lot of work. So I agree with the assessments that the initial implementation was not exactly right. It was actually pretty wrong and terrible, but it was not that easy to fix it. It was a lot of work. So this slides, you will get a copy, has a link to the PRs that implements this with some examples. I personally think that we did an okay job at this, but I do agree that the errors of formatter API that was proposed was not actually very good, and we need to work on that further. As a summary for my long story here, the main message is that our ecosystem today is not exactly helpful with regards to building distributed applications and in the context of error handling. We have fragmented and inconsistent answers to how to do this right. And the new API in 1.13 didn't actually help very well because it doesn't want to know about errors that are not local. But not all is lost. We actually can do something about this and preserve the API. Preserving the API is desirable because you don't want many different errors APIs in your code, and you also want your Go programmers to be able to be effective by understanding only the standard API without having to learn more things. So we should try to reuse standard APIs, but we can still have alternate implementations of the standard API, and that's what we can do here. And that is extending, for example, the semantics of the errors.is and as functions to tolerate errors that come from somewhere else. And the way we did this in this particular approach was to do those identity markers that combine types and messages, can be sometimes customized, to extend that behavior. And then the question we have is that even though it was good enough for CockroachDB, whether it would be good enough for more people, how much we could push to have that generalized to other cases. So that's the essence of the talk, and I would like to thank you for attending. If there are any questions, I will take them now.
Okay, I don't know if I'm being streamed already, but so there are some questions actually. First of all, thank you so much for the talk. It was really interesting, and actually, I am going to look at this afterwards because I have so much beef with the current implementations of errors right now. So. And by the way, you can see applause from all the audience here. So they seem to have enjoyed it. So and the first question we have is, did all of these issues make you think about switching to another language rather than Go? Or was the plan from the beginning just to do something about it yourselves?
That is a very good question. Thank you. From a personal perspective, I come from a very different background than the Go ecosystem. For me, I mean, I do Go for work, but I just have, I do whatever I'm told to do with Go. With regards to doing proper correctness, I would like to have a type system, and Go doesn't provide this to me. So I don't know exactly how to answer this question at a personal level, but with regards to the CockroachDB project, that is a very different question. The CockroachDB project today is too mature and complex to consider a change of programming language. And therefore, even if we were to consider in the future to add additional programming languages or like to make a gradual transition, we'll still have to solve those problems today with whatever infrastructure we have today. So, regardless of whether we change languages or not, we still need to be serious about this in the Go language and do something about it.
Definitely. It's way too big for a project right now. Another question is the implementation bound to protobuf?
So that is a good question. So the proto.message interface is what is needed. So the idea is the following. The errors libraries that we provide says that it can encode objects into something that implements the proto.message interface. And that interface in turn says that it has marshal and unmarshal methods to convert to and from bytes. You could envision a world where those interfaces would be implemented using a different protocols than protobuf. But the case is so that the interface is tailored to the abstractions of protobuf, in particular, for example, that you get loose allocations, like very fragmented allocation on the heap, for example. And so I'm aware of Captain Proto, which is a very different vision on serialization. And if we wanted to use that instead, we would probably want to have alternate implementation of encode and decode errors. However, all the identity marker mechanism and all the other goodies of that library are not tied to protobuf at all. Those markers just need to be preserved by the encoding and decoding functions, and whatever encoding you choose that does this will be sufficient to preserve all the remaining semantics.
Okay, that was actually a very good answer. Another question is, which libraries have you researched that handle distributed error handling very well, even in other languages?
We have an RFC. I added some few links at the end of the presentation when you want to download this. And this RFC link here has a section about a review of the alternatives and what other folk have done before us. And the different pros and cons of using them. So if you want an answer to that, I think the RFC will be better serving than what I can say today, because it's a technical discussion, really.
Okay, that is great. Another question was, which problems did you find with the protobuf implementation?
I think that for what protobuf is designed to do, it does it very well, and I'm not aware of significant major downsides. And that is like ensuring proper, like not pain-free, but like pain-little encoding of arbitrary Go objects that are defined in the protobuf language. And decoding of them and integrating that with RPCs is very good. The one thing that doesn't really work well is that it generates extremely large files, and the integration of that with source control requires, build scripts and so on might be a bit complicated to set up properly, especially when you want to automate the regeneration of those files. There are discussions about how to integrate that in version control, and this is not easy, not as much as we would like. And it also has, for if you have a lot of small objects, it doesn't have very good memory allocation profile. It does create heap fragmentation. And for reference, Captain Proto, which is a different protocol for doing encoding, is much better for that, except that it's not really integrated in the Go ecosystem. So we were not keen to use it, given we already had a lot of protobuf involvement.
Yeah, that actually makes sense. I'm actually not aware of Captain Proto. I never heard of it, but I'm also going to research it after that. So with that concludes the questions we have, unless we have any other questions. Once again, I would like to thank you for your time. I really, really enjoyed the talk. And I think we're going to be kicked out very soon by Hopin. So once again, a very good talk. And thank you so much for your time.
Thank you very much for having me. Have a very good day.